Okay, so we're going to be working with the sine and cosine graphs, and we are going to be dealing with a sine of bx plus or minus c, where we've just decided that a changes the height of the graph, b changes the width of the graph, c is a vertical shift. This is the same a, b, and c, and I'm going to use those in my definitions. So the amplitude, since it changes the height of the graph, is going to be defined to be the distance from the horizontal middle or the x-axis in a regular graph to the highest point on the graph. Tell me something you know about distance. Has to be positive. So if I gave you an equation like y equals negative 3 sine x, what would be the amplitude of that graph? Just as a frame of reference, that graph would look like this. Be 3 high and 3 low. It would still be 3. Even though the coefficient is negative, the distance from the highest point down to the middle is still a 3. It's just that that distance didn't show up first.
So as a coefficient and then a sign, just saying.
So we're going to say that the amplitude is actually going to show up as the absolute value of the coefficient. Is that what you were trying to say?
Yeah.
So it's the positive version of the coefficient, which I think is what Moody was trying to say. Does everybody see where I'm getting that from? Okay, the frequency is how many graphs I will see in the space of one normal graph, or the number of graphs you'll see in the space of one normal graph. And does anybody remember from last class what is the space of one normal sine or cosine graph? When do they usually end? 12 pi over 6, which is the equivalent of 2 pi. So a normal cycle would be 2 pi, and that's going to be relevant to us in just a minute. But which of the numbers, A, B, and C, when we played with the calculator a minute ago, told us how many graphs we would see? It was the B. So B becomes the frequency, and it's a standalone value. B is the frequency. I'm going to move that so it doesn't get confused. So B will be my frequency, and it is straightforward, nothing funny about it. The number of graphs that you will see in the space of 2 pi. Period is a little bit more tricky. Period is where people tend to get confused. What period is referring to is if a normal graph is 2 pi wide and you're telling me you've fiddled with the width of the graph, then this graph is not normal. So okay, I'm going to see 2 of them in the space of one normal graph. So how wide is 1? That's essentially what period is asking. If it's not going to end in the normal place, where does it end? And your job for period is going to be formulamatic. There's not a letter in the equations that's going to tell you the period. What you're going to need to do to calculate period is to put 2 pi, the normal width, over b, which is the number of graphs you want to squeeze into that width. And knowing that trig graphs are all proportional and they are equidistant from section to section, I know that if I just divide a normal space into the number of graphs that I want, they'll all be that big. So when I had 2 graphs in the space of one normal cycle, I'll go back to my calculator for just a second. When I had 3 graphs, let's use that one. So I'll go back up and turn on Y4. Too far. If you had to figure it out, where did that first graph end? 2 pi over 2 pi over 3. Now if I wanted to write that in terms of something that, so when b is 3, period, is 2 pi over 3. In terms of something I can use on a piece of graph paper, you're going to want that to be a pi over 6. Because we've already said our graph paper is going to be pi over 6s, pi over 6s, pi over 6s. So I'm immediately going to change this to 4 pi over 6. What does that mean to me in English? That first graph is going to end at 4 boxes. Now why does that make sense? Because I got 12 boxes and 3 graphs. They're each going to be 4 boxes. Does that make sense? Now it's a good check for you in terms of when you're graphing. How do I know if I'm doing it right? Well, you got 4 boxes out. Did you finish one graph? Because if you didn't, you screwed it up. Is everybody still good? Okay, now the biggest issue with amplitude, frequency, and period is the amplitude and showing it up as a negative. So I'm going to go ahead and do this first one, then you're going to do the next 3. This is the type of stuff you're going to see in the book tonight. I told you it's not graphing. It's just knowledge based on what I taught you today. So they're going to say to you, what's the amplitude? It's the number in front. What's the frequency? It's the number in front of x. What's the period? Take the 2 pi, put it over the frequency, and then simplify, and I'm done. Is everybody okay there? You're going to do these next 9 for examples 2, 3, and 4 right now. Okay, as you peruse these answers, the 2 biggest mistakes that I warned you about, this is one of them. I put it there in a different color so I can throw it away. And that's going to be on a quiz, like next block. That's going to be the mistake that you make in this particular section. Don't make it negative, it's not. See a bunch of erasures. Gotcha already. And that's why I define it as the distance from the highest point to that middle point. It's got to be a positive number. Just keep in mind, always positive, always positive, always positive. Outside of that, the simplification of this thing right here is frequently killer. It's just a complex fraction. Think about it as a flip and multiply, or think about it this way. When I showed you that sine of 1/2 x graph, do you remember you only saw half the graph? That sine of 1/2 x graph right there, it's my y5, showed up like this. Well, if in the space of 2 pi I've only seen half the graph, how far out do I have to go to see the whole thing? 4 pi. Last quick little trick, if you're not really good at these things, as long as that is a 1, your answer is always going to be that number times that number, pi. As long as the numerator of the denominator is a 1, just multiply these 2 green numbers. I think everything else is pretty self-explanatory. The one thing I would say is this answer is just fine. And I would have actually preferred it, but this one is useful for graphing purposes for a self-check. So if you want to write it that way, that's all good. Still good? Okay, before I actually show you how to graph these things, I want you to flip forward 2 pages, I believe, and get into amplitude, frequency, and period for tangent. The Regents has never asked you to graph a tangent. I don't believe they ever will. I will ask you to do 1, maybe 2 on homework, but I'm going to encourage you to try to figure it out, but you may have to use your calculator. I do, however, want you to use the amplitude, frequency, and period definitions without the calculator, and that's because they're pretty basic and very, very similar. In order to get these definitions down on paper, I'm going to ask you to flip back to, I believe it's page 32, to your tangent graph, and take a peek at your tangent graph. Because generally speaking, I'm still going to be defining amplitude exactly the same way, even though I forgot to put it on your notes. The amplitude for a tangent graph is the distance from the middle of the graph horizontally to its highest point. What's the highest point on a tangent graph? Infinity. Well, infinity is not really a single number, it's a place. So can you give me a single number that would be the highest number? No, you can't, because no matter what number you give me, I can go higher. And that means that the answer, this is going to be the big screw up with the tangent graph, for the amplitude of tangent is always, there isn't one. Can you see how that would be screwy? Let me just give you a quick example here. There's not one here, but if I had given you a 0.5 example that says y equals -3 tan x, do you know how many of you would probably put as the amplitude either 3 or, God help you, -3? A lot. There's a number there. You told me the number in front for sine and cosine. The answer for the amplitude of a tangent is now and forever shall be does not exist. Yeah, I'd be okay with that. Emila's asking if you can use the empty set notation. That's fine. Be careful not to make it a 0 because that would be wrong. Frequency for tan stands for exactly the same thing. Looking at that graph that you have of tangent, frequency is how many times do I see this graph in the space of one normal cycle. Well, to do that, I need to know what a normal cycle is, and tangent is a little bit different. So as you look at that graph that you have, how many asymptotes? 2. How many times do you go to infinity? 2. How many times do you go down to infinity? 2. So how many graphs is that? That's actually 2 graphs. It repeats. It starts at 0, goes up to infinity. It starts at -infinity, goes back to 0. Then it goes again. 0 to infinity, -infinity, back to 0. So that's actually 2 graphs. So what is it for a normal cycle of tangent? One cycle. How wide is one normal tangent graph? Just pi. So when I write my frequency for tangent, the definition is exactly the same except for where the normal cycle gets put in. How many graphs will I see in the space of one normal tan graph, which is usually pi wide, and this number is still going to be accounted for with b. So the b in the equation y equals a tan bx does indeed still give you the frequency, the number of tan graphs that you're going to see. Period for tan, same thing going on here. It's still normal cycle divided by b. Notice that normal cycle has changed. So the biggest thing with the tangent graph is don't forget the amplitude doesn't exist, and don't forget a normal period is 1 pi, not 2 pi. So everybody see how this formula is slightly different? Shake your head, yes, I see it. No, I don't. Okay, now I'm going to go back and I'm going to show you how to make a graph. And we're going to do it at the bottom of this page. And in order to do this, I'm actually going to start with some background information. I have my own personal little way to teach these things, and it starts with this. I want you to know the general shape of the sine and cosine graphs. Your sine graph, one normal sine graph, will look like this. That's one normal sine graph. We're going to stop graphing 13 points. And we're going to start just graphing 5 main points, and they are 0, high, 0, low, 0. Those are my axes. And they are 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. And as long as I know that the graph is a curve, if I can get those 5 points down, I can extrapolate the rest of the graph. I like to refer to this as 0 high, 0 low, 0. I've got a lot of kids who turn that into oh holo. That's fine, whatever it takes. That is your sine x pattern. Now worth noting that if I negate the sine x graph, the whole cotton picking thing turns around, and my graph would then look like this, which means my pattern also changes. That pattern would be still 0, but go low, then 0, then high, then 0. Those are going to be the 2 patterns that you need to know for the sine graph. For the cosine graph, we're going to do a very similar thing. The pattern is just ever so slightly different. You don't have to if you can remember it. If not, it'll be on my webpage, but I don't care where you write it otherwise. Is that terrible of me? This one's going to go high, 0, low, 0, high. This is your cosine pattern.